Material Synthesis and Simulation Across Scales Initiative, or as we usually call it, MS3, develops new approaches to making materials that are based on an understanding of the mechanisms by which atoms, molecules, and nanoscale building blocks like proteins or nanocrystals organize. Our goal is to move beyond the traditional focus in material science of the relationship between the structure of material and how it functions. That is, where the atoms need to be placed in order to get a certain set of properties, to a true science of making materials, which is about understanding how to get the atoms where they need to go.
MS3 has really been a game changer in accelerating new collaborations with the University of Washington. For example, my own research program in computational molecular science, I've been able to bring that out here to PNNL and collaborate with a number of researchers who are in the wet lab doing experiments related to synthesis, characterization, and analysis of new materials. And together we're able to make new strides that we wouldn't be able to do individually, coming up with new strategies to make a whole range of new materials.
One of the big challenges in the science of making materials is predicting how the first ordered structures form from the atoms and molecules or building blocks. We call that process nucleation. It's often difficult to achieve because it requires atoms and molecules or these building blocks to come together in a specific arrangement through their random motions. Once they do, they form a pattern for the successive attachment of all the other atoms and molecules. But getting that first ordered structure is the real challenge. Now, in the case of nanoscale building blocks or macromolecules like proteins, we usually refer to this as self-assembly, in part because it leads to hierarchical structures that are organized over multiple length scales, like many of the materials made by living systems.
The approach we take in the Materials Synthesis and Simulation Across Scales Initiative to the problem of nucleation and self-assembly is to connect the microscopic phenomena, which is atoms moving around and interacting, to the macroscopic outcomes of a functional material. To do this, we need a framework to connect the microscopic to the macroscopic, and that's called statistical mechanics. The challenge is that the microscopic theory usually necessitates the use of quantum mechanics, and that contains too much detail. So the challenge for theorists is to try to find the right amount of detail that we can export from the microscopic world to translate into the macroscopic description so that we can really understand the phenomena at the microscopic level.
In nature, there are examples of amazing biomaterials like bone, spider silk, abalone shell, and up till now, humans haven't really understood how to make these types of materials. And here at the Institute for Protein Design, we're learning the fundamental principles for designing new biological materials and actually making completely new types of materials. The partnership with PNNL is really critical, both because PNNL has amazing instrumentation. It's very difficult to do the experiments to characterize the formation of these materials. And just as importantly, they have the expertise. People like Jim DiOrio are really world-class in understanding how biological materials form. They've looked at, over the years, at biological materials forming, and now they're looking at our completely new synthetic materials forming.
We are really excited about the value that a partnership with Pacific Northwest National Labs can produce for us. When we look across the grand challenges society needs us to solve, like energy and water, we're going to be inventing new materials that really lower the cost and energy used to purify waters. It's a critical societal need. We're going to be creating quantum materials that are going to be the foundations of whole new technologies. Everything from how we harvest energy and illuminate the world to new ways to do cybersecurity. When we look at energy materials, the batteries, the solar cells are all materials that harvest or transform energy. And this partnership between UW and PNNL is going to be accelerating that kind of progress. Finally, we're really excited about what biomimetic materials can do. These are materials that are produced at very low temperatures in a very biological sort of manner to lower the energy inputs and improve the performance of materials that go everywhere from membranes for water purification to the materials in solar cells to materials for health.
Well, we believe our efforts put us on a pathway towards making materials by design. And that provides our two institutions, PNNL and University of Washington, with the opportunity to have broader impacts on society through transforming technologies for energy, water, and information.